Okay, so we've talked about equilibrium based on concentrations. We've talked about equilibrium based on gas pressure. Now we're going to talk about solubility equilibrium. And this is all about the equilibrium of a dissolved solid and the dissolved state. So remember back in Unit 3 when we said, we had a bunch of solubility rules, and we said, oh, this compound is insoluble, this compound is soluble, right? So those solubility rules are oversimplifications. Okay, so they're kind of just a way to make moving through lots and lots and lots of reaction types more efficient. But the solubility rules are, when it comes down to it, are not very precise. So if we say something is insoluble, those solubility rules are based on whether or not you can make a 0.1 molar solution. If you can dissolve 0.1 moles of solute per liter, then we call that soluble, according to those rules. Now, the reality is everything is soluble to some extent, some more than others. Some substances you can dissolve more than 0.1 moles. Some substances you can only dissolve, like a billionth of a mole. All right? So rather than just use a rule like it is or is not soluble, now if we have the solubility constant, we can actually solve for the exact concentration that something can be made. So first, let's talk a little bit about solubility equilibrium in general, though. Let's say that we have a solution, all right, and let's say that you dissolve something, right, and so it's a solid, you mix it, stir it, right, and after stirring it, you still have visible solid, even after lots and lots of stirring. When this is the situation, if the solid is visibly present, that means you have dissolved as much as you can. Right? There's a term for that. What is it?
Saturated.
Yeah, it's saturated, right? Well, saturated means in equilibrium with the solid. So if the equation were to look something like this, if you see the solid still there, then we have a system at equilibrium. All right. Now, a couple more things about solids. If the solution is at equilibrium, and we have the maximum amount of dissolved solute, if I dump a whole bunch more of solid in here, right? Let's say I just keep chucking in more spoonfuls of that same solid. That concentration of the dissolved state does not change. Adding more solid does not shift the equilibrium. You guys understand that? It's like you can only make a sugar solution so sweet by adding, there's a certain point where you can't dissolve any more sugar, right? By adding more sugar doesn't mean the liquid part, the dissolved state, is actually any sweeter. It just means there's more solid sitting at the bottom of the cup. Okay, so adding more solid does not shift anything. It just means, there's more solid in there. That's all it means. Okay? All right, so because this is an equilibrium problem and the mechanics of the equilibrium process are the same, they're universal, we go about these applying the same logic that we had in all equilibrium problems. Things like how to set up a law of mass action, products over reactants. Things like we cannot use concentrations of condensed states, so solids and liquids must be ignored, right? Setting up ice tables. It's all done the same way because really these are all equilibrium, so they all work the same way. So let's take this first example. So we've got silver nitrate and sodium chloride that are mixed together. So we mix these two together, and then we have both chloride and silver ions in solution. Now, traditional rules say that silver nitrate is insoluble, but we know that's kind of a distortion. It's actually soluble to some amount. So in any solubility equilibrium, you've got to first write the reaction, but you write it from the perspective of dissolving the solid. All right, so solid on the left, dissolved state on the right. Okay. Always start with your solid on the left. So, writing a law of mass action for this. Right, no surprise there. Products are reactants, but you can't use a solid. Now, the equilibrium constant. Oh, by the way, the constant is called, the KSP is the solubility product. All right, that's where K of SP comes from. It stands for solubility of product. Okay. All right. So, if the KSP is known, we can go ahead and solve for what the concentration of these ions is at equilibrium, i.e. when it is saturated. Right? So, 1.6 times 10 to the minus 10th is equal to, we'll just call, actually, you know what? They use the value, the value S. Guess what S stands for? What is it, Ron?
Solubility.
S is the solubility in molarity. Why is it called solubility product? You're multiplying S by S. Okay, so that's where KSP comes from. So to find the solubility, all you need to do is take the square root in this case. All right, so we get 1.3 times 10 to the minus 5th molar. Now, you probably could have arrived at this value without me even talking about solubility product constants. You probably could have just looked at this, set up a law of mass action, seen that the constant of K was given, and solved for S. Right? Again, the mechanics of the equilibrium problems are essentially the same. Let's try another one, lead chloride. So lead chloride, PbCl2, the formula makes a huge difference in the polynomials and how the problem gets set up. Because as you know, when there are subscripts in the process of dissolving, these dissociate, and when they dissociate, it becomes a coefficient. Right? So here, now, if I said, okay, let's set up a law of mass action for this, but actually, before we even do that, I'm going to set up an ice table. Okay? So nothing registers underneath the solid. We are starting with 0 concentrations. But the point of the ice table is to point out that the chloride will increase by a factor of twice the solubility because of its coefficient. So now, when you set up KSP expression, it should look like this. And so after you substitute in what you called the equilibrium values into here and into here, you now have this. And it seems like such a simple thing, but it is so often, people make mistakes so often because they either forget to bring the 2 over, right? This 2 over here, oftentimes people forget to bring this over here, or they might forget to square it. You're doing both. You're bringing the 2 over, and because of the way you set up the law of mass action, that quantity must be squared. So you got to do both, basically. All right, we don't really need a solver for this because this is going to be equal to 4s cubed. All right, so really what you're doing is you're dividing by 4 and you're taking the cube root. I mean, you could use solver if you want. Okay, it's not necessary. All right, so solubility is going to be 0.016 molar. Okay, how are we doing? Finding the solubility if given the KSP. All right. So, more examples of problems that we might see. If you know the concentration of one ion, you know that of the other. And that's because of stoichiometry. Right? Mole ratios. if I give you another example and I said the concentration of lead, we dissolved some lead chloride. The concentration of lead is, or sorry, let's go do this backwards. If the concentration of chloride is 0.02 molar, what's the concentration of lead? Well, 0.02 molar of chloride. The ratio, of course, is there's one lead ion for every 2 chlorides. So the concentration of lead would be 0.01. That's all it is, right? Stoichiometry. Okay. Determining whether a precipitate will form, and this is probably the more directly the application that you're going to be using this for. So, remember how in a regular equilibrium problem, if you didn't know which way the reaction was going to go, like if you didn't know if you were adding the x's to the right side or the left side, you would have to solve for q first, right? And then you would compare q to k, and that would tell you which way the reaction goes. With precipitation problems, it's the same thing, except we use p instead of q, right? But it's mathematically the same process. If p, here, let's use an example. I'm going to add a page. Okay, using the example from above, where do we have a KSP? We had a KSP of lead chloride, right? So let's write off that example. The KSP was 1.7 times 10 to the minus fifth. Did I get that right? I wrote that really fast. Yeah, 1.7 times 10 to the fifth. Okay, so PbCl2 solid was Pb plus 2 plus 2Cl minus. Okay, let's say that we mix together solutions to the point where we have initial concentrations of lead to be 0.005 molar and the chloride to be 0.008 molar. Okay, let's say that these are our initial concentrations. The very first thing I need to do is figure out which direction this equilibrium is going, because I have no zeros in my initial row, so it is not obvious which way this is going to go. So we solve for P. And P is taking the concentration of Pb initial times the concentration of chloride initial quantity squared. So 0.0050 times 0.0080, that's going to be squared. What do we get? Okay, so 3.2 times 10 to the minus 7th is what P is. Now, as you can visually inspect, P is less than KSP, which means not enough product is formed, and in a solubility problem, the product is the dissolved state. So there's not enough that is dissolved, which means more has to be dissolved. So this is going to shift to the right, which means we will be adding to the right side. And so we can find the equilibrium concentrations by doing what we always do. Set up the law of mass action and substitute. And here I would use the solver. Now, your calculator does not have S. You just use X in your calculator. Make sure you use the coefficient of 2. And also make sure you square it. All right, solubility is 0.012. Which means the actual final concentrations, you have to adjust. So 0.005 plus x. So this will be 0.017. 0.008 plus 2x. And this will be 0.019, 0.20. Okay. All right. So determining if a reaction is going to dissolve more. If it's going forward, it's going to dissolve more. If it goes forward, we do not see any solid because it is not at equilibrium. Make sense? The only way we see solid or cloudiness is if this reaction is prompted to move backwards because the reactant is the solid. Okay. And we'll do maybe another one. Suppose silver ion is added to a concentration of 0.001 molar. Well, this is awkward wording. I think suppose the silver ion concentration is, right? Suppose silver ion concentration is 0.001 molar, and the solution of chromate is 0.001 molar. The silver KSP for silver chromate is given. What will precipitate form? Okay, this was awkwardly worded, but they're basically telling us as the initial concentrations of both. So to start any KSP application problem, what do you start with? What do we need first? We need the equation. Silver chromate, Ag2CrO4, solid, dissociates 2 silver ions and chromate ion. All right. They're giving us initial concentrations, so P is equal to the concentration of silver initial times chromate initial. Don't forget to square the silver. Okay, so let's plug and chug. They gave us the initial concentrations of both. All right, so 1 times 10 to the minus third, you're going to square it, then you're going to multiply it again. So effectively, we have 1 times 10 to the minus ninth. Which, of course, based on the KSP they gave us, is greater than KSP. That means there's too much product. This reaction is going to go backwards. Will it precipitate form? Yes. Precipitate forms because the value of P is greater than KSP. Putting the cart a little bit before the horse here. Maybe I should have done this third example before I did the last one. Primary use of KSP is not only to determine whether something's going to precipitate or not, but also to determine what the concentration is at equilibrium, i.e. what is the solubility of something, right? So maybe if we were trying to figure out the solubility, all you need is the KSP. So I think we just did this one, right? Didn't we determine the solubility of lead chloride earlier? Or was it? I think we did it here, right? Here we determined solubility is 0.016. So we don't need to do this one again, but I'm going to give you a new one. All right. So I'm going to make up a fictional value because I don't have my table of solubility constants in front of me. So we'll say that we have a compound QR2. Oh, wait, no, we'll go crazy. QR3. QR3. All right. So QR3 dissolves. We get Q ion and we get 3 of the R minus ions. The KSP for this is 5.5 times 10 to the negative 16th. Now, by judging that by that KSP, you might say, look how small that is. This must be really, really, really insoluble. But you have to be careful now because consider now you have a cubic function in your law of mass action. So it could be deceiving. To determine the solubility, you can't just judge it by a KSP alone. You must always solve for it. So what would the rest of this look like? All right, our KSP expression then would become this. And so after substitution, which is going to be this. So, I mean, you don't need solver again. You can just divide both sides by 27 and then take both sides to the 1/4 power. Oh, wait, I wrote the wrong number. That's 16. There we go. So the solubility will end up being 6.7 times 10 to the -5th, which is small, but it's probably not as small as you were thinking it would be, given how small the initial number was. All right. So can you solve for the solubility given any compound's KSP? I know that sounded rhetorical, but I was actually asking the question. You guys feel comfortable doing that? Solving for S. Okay. Can I give you initial concentrations and you solve for P and determine whether the reaction will be going to the right or to the left? Yeah, it's just like solving for Q. Okay. All right. You know what? We're going to stop here. We'll pick this last little bit up later because I want to finish our lab.